And I just want to get back to the basic idea of the frequency response as a thing by itself, which is simply that if we have a system and that system is a linear time invariant system, LTI system, the kind of systems that we are pretty much always analyzing in the subject, if I were to subject that system to a pure sinusoidal input, it would respond by outputting a pure sinusoid eventually, remember, right? So there's this kind of a transient period because actually when we input these sinusoids, just like every signal that we analyze in this subject, the assumption is that that signal used to be zero forever. And then at time zero, it starts doing whatever it was doing. It's either a step or a ramp or whatever, but it's not that in the negative time area. In the negative time area, everything is zero. So things start from the steady state. We then start a sinusoidal variation, and the output of that system then eventually settles into a sinusoid after some transient time. So there's this kind of transient time, and then after a while, at some point in time, there's now a pure sinusoid. Right, so this is now the underlying idea behind frequency domain techniques, is that it is possible to calculate that sinusoidal response using the Laplace transform, or in our particular case, we're going to effectively be saying we use the Laplace transform with this kind of substitution. So remember, we had the Laplace transform of f of t, which was defined this way. Right? And effectively what we're going to do is we're going to say a way of calculating the Fourier transform is the same integral. Actually, the Fourier transform is usually bilateral. So it's f of t e to the minus I omega t dt. And so this Fourier transform, you will remember that you came across the Fourier transform when you were doing Fourier series expansion, because the Fourier transform was basically how you figured out the coefficients that you would add to the various sinusoids that you added together, or the sinusoids and cosines that you would add together to get the approximation, the Fourier series approximation. And so if you look at those two definitions, one below the other, you basically find, oh, okay, so the Laplace domain, right, the Laplace kind of lives on this S-plane, where we could say, well, this is the imaginary value of S, this is the real value of S. And you can say, what is the Laplace transform? Well, the Laplace transform is this complex valued function. So g of S is a function which takes a complex argument and returns a complex result. And the frequency domain effectively lives here. Right? So that positive real part of the Laplace domain, that's the section that we're taking to get to the Fourier transform, or to get into the frequency domain. Now, just if you are kind of trying to do the comparison between the Laplace and the Fourier transform, just remember that the Fourier transform definition often has factors of 2 pi in there. It doesn't make any difference to the qualitative explanations that I'm going to use, but you'll find definitions of the Fourier transform that have 1 over 2 pi in the beginning, and it's normalized on a period, and there's a lot of extra kind of, but it's all constants. It doesn't change the nature of the transform, it just changes the values. So, I like this kind of equivalence where you can say, well, I get into the frequency domain by setting S equals to I omega. And so this is actually one of these wonderful things where you can say, well, experimentally, I can do the sinusoid, and we're going to do that in the tutorial. I can actually subject a piece of equipment to a sinusoidal forcing. I can observe the sinusoidal output. I can see what the angle or what the phase difference and the magnitude difference is. And if I do that experimentally, and if I compare that with what I get by just plugging this in, I will find that the phase angle, now just to be sure that everybody understands, so I've got my input sinusoid and I've got my output sinusoid of some different magnitude. And you can kind of say that there's this kind of a phase difference over here. So that is called P. And I want you to understand that this is now, that's time, right? And so the input magnitude and the output magnitude are read off over here. So in many cases, we can kind of normalize that to 1 as the input magnitude. And then we can kind of talk about what is called the amplitude ratio, which is the ratio of this amplitude to the input amplitude. Okay, so there's two kind of concepts. The one is this idea of amplitude ratio, and we're going to see that that's given by just the magnitude of g of I omega. And then so that's the ratio of those two magnitudes to one another. And then this phase here, we're going to say this sinusoid over here is actually given by some amplitude times the sine of omega t minus phi. And I want you to notice there that I didn't write minus p, because the units of phi is in angular units. In other words, it's the target of the sine, right? So omega times t has units angle. If we were working with degrees, like omega t, omega is angular per time, so like radians per second, right? And so omega t has units just angle. And so phi also has units angle. But p over there, that phase difference that I drew there, notice that has units of time. And so that is not phi. That difference, that shift there, if you're drawing it on an axis, and the x-axis is time, just take careful note that that is not an angle, or an angle. It is a time. And so obviously you have to work backwards from that time back to the angular equivalent. And you can kind of work backwards and see that you need to go, so if it's time, I need to divide by, I've got the time, I need to divide by the time, or effectively multiply by the frequency. Right, remember, because frequency is angle per time. If you just think about the units, you can see that you're going to have to multiply that time shift by the frequency to get to the angle equivalent. Is that making sense to everybody? Another way of thinking about this is that the equivalent formula here is that you've got I sine omega, and if you think about what shifting on the time axis is doing, it's replacing t by t minus p, right? If you're shifting. So the equivalent formula here would be t minus p, and notice that that's now, it's omega times t minus p. And that, I think, makes it very clear that p is doing a time shift on the sinusoid. Does that make sense to everybody? Right. So that's kind of the basics of frequency domain. That's basically what the frequency domain is. And we're going to think about the frequency domain in these two discrete ways. We're going to think about it as an actual physical response on the one hand, but we're also going to think of it mathematically as just what I get when I do the substitution and I plug in a lot of different frequency values. And so you'll recall that we have a couple of, oh, I didn't actually finish this. So there's also, we're going to see that that phase angle is just going to be the angle of G I omega. Right, so remember that a complex number, so there's a vector here that is called G I omega. That's the angle, and that's the magnitude of that complex number. And you thought you would never do complex mathematics again. We're going to do a lot of complex mathematics. Now, I want to just raise a flag here because in these early parts of the textbook makes it look like you should be using, let's say, the formulae that they use to derive the various properties to do the derivation. Now, I have never in my entire life set a test where I expect you to use the formulae in the book that they use to calculate the phase angle and so on, right? What I expect you to do, because you're sitting in front of a computer, right? So the formulas in the book are like, let's play this game. Let's imagine computers didn't exist, right? Then we could do all of these tedious calculations by hand. Wouldn't that be grand? And my answer is no, it would be terrible. It would be much nicer to just substitute S is equal to I omega into the formula using the computer. You can even do that analytically. That works fine in SymPy. But if you're doing it numerically, you just do the substitution. Python is perfectly capable of doing calculations with complex numbers, and you get a complex number out, and if you want to know the magnitude or the phase of that particular component, you just calculate it using abs or angle. Right, so in Python, that is the abs function, and that is the angle function. So very, very straightforward. I'm saying this for the first time because I always thought it was so obvious that these formulas are basically impossible to memorize and equivalently incredibly tedious to work with. So I thought I didn't have to warn you that you shouldn't be memorizing these formulas and working everything out by hand. But what I've noticed is in these tests, I see, and it's closed book tests, but people have for some reason committed these formulas to memory like a boss, right? They are 100% not necessary. I highly recommend that you rework these problems without using those formula, and just using, if you want a numeric answer, using NumPy. If you want a symbolic answer, using SymPy with the substitution. SymPy does all of that stuff for you. Just like I didn't expect you to memorize the Laplace table, I do not expect you to memorize any of the frequency response formulas here. Well, when I say any, what I mean is I don't expect you to memorize the actual results, the analytic results that they have. I expect you to know the things that are important, which is these concepts. So I expect you to know what the definition of phi is. What is phi exactly? It's this thing, right? It's this shift that we obtain in this case. That's important. So don't call me and say but Carl, you said that we didn't have to memorize formulas, and I completely didn't know that this was the definition of how a shifted sinusoid looked. Please still do that. That's important, right? But I'm talking about results like equation 13.3b and worked out results where you analytically follow through what these results are going to be. Those things are, I think, considerably less useful than knowing how to do the calculations with the tools that we're going to use. So another set of important things to know is how we normally represent these things, right? So we have a couple of diagrams, and the most important one that we're going to be using a lot of the time is a representation of the frequency response called a Bode diagram, where I have the gain and angle of G on two separate graphs. Conventionally, they are logarithmic in frequency, right? So this is usually logged. And then the magnitude part of that Bode diagram is also typically logged. And the angle is typically just not logged. And so these diagrams are related in this very special way. So we're going to use two kinds of diagrams. For the first time, unlike in CPN, we're going to use a second kind of diagram in this subject, which is called a Nyquist diagram. And Nyquist diagrams are maps on the complex plane of the frequency response. You read frequency effectively that way. And so I want you to kind of see that there's this equivalence that, for instance, here at this low frequency area here, so this area where this low frequency is over there corresponds with that point on the Nyquist diagram. I hope everybody is following what's happening over here, right? So at that point, at that frequency, I have a frequency response, a single valued frequency response, right? I can go and calculate using those formulae, and again, not using the formulae in the big formulas with like square roots and sines and stuff, but literally just like calculating the frequency response and then calculating the magnitude or the angle of that complex number. That's what gives me the magnitude over there and the angle over there of the system when evaluated for omega equals some low value, right? If I look at this, so the gain here clearly starts high and then kind of stays roughly the same and then goes very small. Remember, this is a log axis, so when this thing goes like that, it's not intersecting with zero. It's going towards zero asymptotically. So kind of a straight line going down on a log graph like that is actually kind of asymptotically going down to zero. None of these magnitudes are ever less than zero, for obvious reasons, right? Because we can think of it as the magnitude of a vector, or with the sinusoid as well, like there's no meaningful way to interpret the amplitude ratio as a negative number, because when we look at that output sinusoid, it's always going to have an amplitude of at least zero. It won't, like, there's no way to say that sinusoid has an amplitude of -5. Okay, so we know that the amplitude is going to be bounded by zero. It's never going to go less than zero, right? So now think about what's happening. So that's that point. Then we have, as the frequency increases, so effectively, that's the point that corresponds with the very low frequencies over there. And so we start with the low frequency, we then increase the frequency, and as the frequency increases, you can see that the line is getting closer to the origin, which means that the magnitude of that complex number is getting less. And you can also see that the angle, which is defined as the angle which is made with the positive real axis in a anti-clockwise direction. So it's the kind of that math definition of angle that you had to learn, right? So remember, I've got a little diagram over there. Remember, so that's the angle over there, right? And so these we all interpret as negative angles. Okay, so we say, well, it started at an angle of 0, and then it kind of went all the way. And you can see the asymptote there, even though the magnitude of that size, or the complex number is of 0 magnitude, it's coming in from the bottom, right? And so we can say it's got an angle there of minus 90 degrees. And so we can see that you can kind of, if you construct a Bode diagram, you can easily construct the equivalent Nyquist diagram by reasoning through and effectively just sweeping a horizontal line across that axis. And as you sweep the horizontal line across the axis, it'll sweep out this curve. And so you can kind of say that the Nyquist diagram is like the locus of the G of I omega. Now, there's another kind of diagram which we're not going to be using in the subject, but just for completeness, which is called the Nyquist Diagram. Now that actually is very useful to predict, well, it used to be very useful to predict the closed loop behavior from open loop behavior, again, in this very weird time when nobody had computers. So just notice that there will be kind of people saying Nyquist diagrams. I'm not going to even tell you what they are, but you may just have heard about them. We're only going to use Bode and Nyquist in this subject. Now, the specific reason why we're going to use the frequency response, and the reason why, and I kind of want to kind of use this lecture to just attune you to the things that are important to me. So I think here we already have like the things that are important to me in terms of like knowing what is the frequency domain at all. If a control engineer says, I want the frequency response of a system, this is what they probably mean is one of these diagrams at the bottom. So they're going to say, do you know what the frequency response of that system is? And if you do not have one of these plots, you will say no. But it's trivial to get to one of these plots if you have a transfer function, right? Very, very straightforward. Now, why is this useful? So the first part is open loop interpretations. And so the frequency response tells us a lot about the system, and it allows us to interpret the system as a filter, like we spoke about in CPN when we spoke about the way that filters affect sound. So you've heard me say this a couple of times in class as well, where I say something like a tank, which is a thing that has a frequency response like this thing that you are seeing at the bottom there, right? So that looks very much like a first order frequency response. We will describe that as a low pass filter because it leaves the low frequencies unchanged and it attenuates the high frequencies. And so by convention, we kind of we use this idea where we say, okay, and now for first order systems, that frequency at which things happen is called the corner frequency, and it's actually 1 over tau for first order systems. I very strongly encourage you to at least have some skills of drawing these things asymptotically. And so you can kind of say, well, there's an inflection there, and you can go in the textbook and see how these asymptotes are derived. I will never expect you to derive the asymptotic formulae yourself. They are obtained very straightforwardly by just using limits, right? So you basically take the formula for the actual frequency response, you let omega go variously to 0 or to infinity, and you look at the shape of the formula that you end up with. It's useful if you are mathematically inclined to just like justify these asymptotes, but from a practical point of view, the thing that I expect you to know about these asymptotes is that they exist and how to draw them. The reason why I want you to have that in your head is because these asymptotes allow you to close your eyes and picture what the frequency response will look like in ways that are completely inaccessible to you if you are actually using the math to get them. It is super easy to remember what these things look like. Basically, if you know what the first order one looks like, you know all the others automatically except for underdamped pole pairs. So there's only two kinds of behavior, right? There's the behavior associated with real poles, and there's the behavior associated with complex poles. If you think about it in terms of the kind of thing that you would encounter in real systems. You can't infer the complex pole behavior from the real pole behavior. So that's new. But there's nothing beyond that. There's no special fourth order behavior. There's first order behavior like this, and then there's the undamped pole behavior, which looks like this. Now, actually, let me just make sure that that's drawn correctly. So that angle here is -1 per decade, and this angle here is -2 per decade. Or that slope. So that's what that looks like. This is what happens. Again, it's at tau, and this, what they call the harmonic nose, gets more pronounced as zeta gets smaller. So in that direction, there's like zeta. So this is for a second order system. Now, what is also important to me is that you understand how the log rules work. And this is especially important with Bode diagrams, because Bode diagrams are constructed in the way that they are constructed in order to allow them to be manipulatable in your head really, really easily. Why? We will often encounter systems in series. And if I know what the frequency response is of each one of those systems separately, calculating the frequency response of the overall system involves calculating the frequency response of a product of different complex numbers. And it's important there to understand that the gain of G1, G2, G3 is equal to the gain of G1 times the gain of G2 times the gain of G3. You'll hear me say gain and magnitude kind of interchangeably because those things are so strongly related, right? So that's not very useful unless you realize that we are often going to plot these things on log axes. And then it becomes really useful because of log rules. So you'll remember this product log rule, which says if I take the log of a product, the answer is the same as the sum of the logarithms of the separate items. And what that means in practice when I'm drawing the Bode diagram is it's really easy, well it should be easy, to picture what the sum of curves look like. And so if I have a Bode gain diagram that, for instance, looks approximately like this for G1, and I have a thing that looks approximately like this. So let's say that starts at 0, and then this starts now on log axis, right? So remember that the value 1 has a log of 0. So when I say 0 like this, I'm usually talking about log G1. And if I have log G2 over here, magnitude, log of the magnitude, and if I have something like that, and let's say that thing has a gain of 10, say. So that's the log there is 1. And I have another gain over here, and that looks like that. I can very easily picture what that product will look like because I can reason through these straight line parts. So I can say, in this region, I've got a straight line plus a straight line plus a straight line, right? And that will give me a straight line. In this region, I have a -1 per decade down, plus a straight line, horizontal, horizontal, which means I'll have a -1 per decade over here. And then I'll have a -2 per decade in this region over here. Because there I've got a -1 per decade, a 0 slope, and a -1 per decade. And so I hope by now that everybody's looking at that and saying, well, yes, that is super obvious, right? Like adding, definitely picturing the sums of piecewise linear graphs should be, at this point to you, entirely trivial. It's important because I'm going to ask you to call to mind the frequency response of systems, and I'm going to expect you to be able to do that faster than you can type the code into Python. Especially when I consider something like, if I ask you, so what will it do to the overall, what will happen to this overall graph if I change the gain of that second system to be, instead of 10, to be 1? What will happen? That whole curve will move down, right? And so I will be asking you to do that in your head a lot. I'll draw a couple of them for you initially, but a lot of times I'm going to be thinking it will be obvious to you that increasing the gain of any one of these blocks will move the whole curve up. It should be obvious to you that, like, doing this to this curve, moving the corner frequency will have this kind of effect on the graph. Those things, if they are not obvious to you now, take steps to make sure that they become obvious. Probably if you really want to, like, just do exercises, choose a couple of straight line segments, make them in Python, add them together, see if you could predict the result properly. Right? So you can easily construct an infinite number of example cases for yourself just in Python and verify that you can get the answer right using only your head. Now, a similar thing holds, also, like, thankfully, a similar thing holds for the phase angle. So it is true that the angle of a product is equal to the angle of each one of those things added together. Now, I'm writing all of this down because this is the stuff that, like, this is super important. Knowing that these relations hold is incredibly important. Because if you don't have these completely intuitively in your head, a lot of the stuff that we're going to be doing when we draw Bode diagrams or interpret Bode diagrams are not going to make any sense to you at all. They're not hard concepts. They're built to be simple. And the Bode diagram is built to exploit the simple way of doing these calculations. So this is why the Bode diagram has log on the gain. This is why the Bode diagram doesn't log the angle. Because Bode diagrams are constructed in such a way so that products of systems are easy to construct using no special machinery. If I have each of the separate Bode diagrams, I can easily imagine what the product will look like. Furthermore, if I know my log rules well, so these are like a first couple, but it should be, I hope, obvious to everybody that if this is if I have a frequency response like this, which is associated, if the magnitude of a frequency response for 1 over tau s plus 1 looks like this, then the magnitude of a frequency response for tau s plus 1, I want you to understand that it's obvious that the frequency response of the inverse of that signal looks like the way that I've drawn it. Why is that obvious? Why is that obvious? Because the log of x to the minus 1 is equal to minus 1 times the log of x. Metric log rules, right? This is not even university level stuff. But I want you to understand that this is a simple consequence. Don't waste time memorizing the table in the book in detail. There's a table of known frequency response in the textbook. I strongly recommend that you take all the time that you would have taken to memorize those responses and make sure you understand this thing that I'm telling you now, that the first order response and the complex pole pair response, those two things together, because there's no way to go from like a real pole frequency response to what a complex pole response looks like. That's completely new, right? Those two things together plus log rules covers the entire table. Literally the entire table. Why? Because the inversion, straightforward. Okay, those two things together cover the gain part of the entire table. Right-hand plane zeros have a weird phase response, and I'm okay with it if you just memorize that. But let's say those three things, right? So real poles, right-hand plane zeros are weird, but those three things, if you memorize all three of those things, that's the only stuff you actually need to memorize. What a first order response looks like, what a second order response looks like, and what a right-hand plane zero looks like. And because right-hand plane zero is just the phase is weird. Well, the phase goes the opposite way from what you expect. So the way that you can kind of infer these things is that, for instance, for a first order system like this, right? A first order system like this with a very large time constant is almost exactly like an integrating system. Does that make sense to everybody? So when tau gets large, so when tau gets very large, that one isn't really contributing that much. And so this whole term starts looking a lot like 1 over s, or 1 over some constant times s, which means that I can expect what an integrator will look like by saying, well, it's like a first order system, but with the corner frequency way over to the left. And I would be right, because an integrator is just a diagonal line going down from left to right. Okay? Same thing goes for a differentiating system. You can get there two ways. You can say, well, if I know what an integrator looks like, and I knew what an integrator looks like from reasoning through this tau thing, and I know this log rule that's on the screen right now, that makes it obvious what a differentiating unit, what an ideal differentiating unit would look like. It would look like a line going with a positive slope instead of a negative slope. Do you see this all follows, right? So you can get to most of the stuff in the table by just reasoning through those basic systems. The last thing that you do need to also commit to memory is the effect of dead time. So dead time being an exponential obviously doesn't resemble any of these other things, and so you just have to remember that dead time doesn't affect the gain, but it has this infinitely decreasing effect on the phase. Now, once you are there, once you are able to construct these Bode diagrams in your head, I want you to go and look at my frequency domain stability video on YouTube. So I linked to it in one of my previous videos, but I'll put a link in again. That explains the last part of the reading. That was actually the reading for today. The reading for today is, how do I use the frequency response to assess the stability of closed-loop controlled systems? And it turns out that using frequency domain techniques, and kind of uniquely, I can use frequency domain techniques to predict the stability of closed loops without calculating the frequency response of the closed loop. And this is kind of the party trick that we use the frequency domain for in control. It's the thing that allows us to avoid evaluating the closed loop transfer function. And so there's kind of these whammy upon whammy. So because you get the fact that you have, from the straightforward frequency response of just the system and the controller, which you can usually picture in your head really easily. You can then construct the forward loop transfer function in your head because you're just calculating products which on Bode diagrams look like sums. And then you're done in terms of what you actually have to do. You can do all of that basically in your head. You can reason through it in your head. And if you understand the application to the stability criteria, which I'm not going to go through now, but which are explained in much more detail in this other video, that I'll also link to it in this video. That means that I can avoid all the difficulty that I was having to do with stability calculations in the Laplace domain, where I had to calculate the nature of the poles of the closed loop transfer function. Here, I don't even calculate the closed loop transfer function at all. I don't calculate the closed loop transfer function frequency response. I don't calculate anything other than the frequency responses of the separate systems and the forward part of the loop. Then I'm done. So it's hugely beneficial, and I find that the frequency domain lends itself the most of all of these different techniques to intuitive reasoning about the effects of control changes, which also means that by extension, it's the part of the work that you hate the most, because it's the part of the work that has the fewest set pieces. There are very few, like, do the work kind of problems here. I typically, if you are in the mood for making notes about like how this will be assessed, the frequency domain, by and large, in my tests, are the place where I ask for insight. Because the calculations are very easy. Very, very easy. They're very simple, but the application gives you great insight intuitively into the system. So you need to kind of make sure that you are developing that intuition and not just the mechanical skills of drawing these diagrams. You're probably not going to get any credit for drawing an actual Bode diagram ever in this subject, but you'll get a lot of credit for understanding what they mean. Cool. Thank you very much. I will see you in the tutorial.